Okay, let's get started. Let's talk a little bit about the deliverables. We're in the trenches now. Quite a bit of work. How many people got deliverable 4 in? Looking pretty good. Okay, who started on deliverable 5? No one quite yet. Okay, let's. I just want to talk about deliverable 4 for a moment. Is Gabe here? Hi, Gabe. So Gabe very generously agreed to allow me to show his solution to deliverable 4, which is not quite correct. That's not what we're going to focus on today. I wanted to show Gabe's submission to help you understand why you're submitting things as video and images. So the video and images obviously makes it easier for us to help identify what you've got right and what you've got wrong. But it should also be useful for you, especially as we go forward into the later deliverables, to help figure out where the problems are in your own code. Right? We spent quite a bit of time in this class talking about visualizations. Use your visualizations to try and work backwards and find where the problems are in your code when they arise. So if you create an image or you create an animation and you're not getting what you expect, why? What is it that's surprising about the visualization, and what does it suggest about where the problem is? So without picking on Gabe here, there is something that's not quite right here. What is it? And also, this was the first deliverable where you're submitting something where you don't know what the actual image should be, right? But hopefully, if you've digested enough about how KNN works, and how these visualizations tell us whether KNN is working or not, we should be able to figure out where the problem is in the picture and at least start to go back and have a guess for where the problem might be in the code. Any ideas?
It looks like the inside of the dots on all of the test ones are blue.
The inside of the dots on all the test dots are blue. Right. Okay. To my eye, everything else looks correct, right? Things that are encircled in black is the training data. That all looks fine. What about the edges of the test data? How does that look? So we talked last time, and it was my fault. It's not clear from the instructions. I think I switched it, right? Whether your prediction is the edge color or whether your prediction is the face color. So in Gabe's implementation here, is the edge color representing the prediction or the actual iris type? And how would you know? Right? Again, we're trying to visually inspect this image and work backwards to where the problem might be.
Probably the actual iris type, because there's actually different colors there.
So there's actual colors, right? So all the edge colors here that are non-black are all pink. And all of the edges that are green seem to be near all the green, and all the edges that are in blue are near the actual blue, the training blue, which makes me think, Gabe, that you're plotting the edge color, which is representing the actual iris. Do you think that's what's going on in your code? Okay, so now we're narrowing in, right? There's nothing wrong with the training data. There's nothing wrong with visualizing the actual test data. There's something wrong in the predictions, right? So they're all blue, which suggests to me that the predictions are either all outputting exactly the same class, or maybe you're not actually using the prediction to color the internals of the points. And we won't go any further than that, but again, I just wanted to use that as an example for what you should be doing as we move forward in the deliverables, right? Use these visualizations to sanity check your system, right? Is it actually correct? You should be able to figure it out, or at least use the visualization to narrow in on where things might be going wrong. Okay, so far so good? Did most people in Deliverable 4 manage to get a KNN that was making pretty good predictions? It was right for most of the cases? Okay, So that just made you that much more employable when you finish here at UVM. If you can walk into a job interview and talk intelligently about the KNN, the nearest neighbor algorithm, employers like to hear that kind of thing, right? Maybe your employer is not interested in classifying different types of flowers, but if your employer says, here are all the products we've ever deployed, and here are all the products that sold very well, and here are all the products that failed, and we don't know why, this is where the money is to be made, right? Can you actually, what can you predict about what kinds of products and services a company is likely to succeed with and fail with and so on, right? This is just part of what's making the big data revolution such a big revolution, right? It's data with these algorithms, all right? So maybe you're not that interested in flowers, but if you're interested in a job, KNN is quite useful. Okay. So that's deliverable 4. Let's talk about deliverable 5 for a moment. Okay, so deliverable 5, 9 pages and 47 steps, so pretty long. The big challenge in deliverable 5 now is you're going to now be recording data, and you're going to be sending it to us. You're actually going to be submitting data sets now at the end of deliverable 5 rather than submitting images and videos. When everybody submits their data sets from deliverable 5, the TA is going to package it all together into one big data set. We'll put that big data set online, and then in the later deliverables, you can download that combined data set and rerun it through the KNN algorithm that you developed in deliverable 4. So we're going to swap out the flowers, and we're going to swap in all of the gesture data from all 37 of you, and hopefully, and we'll be tuning the KNN algorithm to make sure that it can work with all the sizes of hands and righties and lefties, and those of you that wear jewelry on your hands and those of you that don't in this room. Right? We'll see how we can do, and we'll work on that. Okay, so how does this work? I'm going to just point out a few things where things can go wrong in deliverable 5, pitfalls to watch out for. You'll notice right at the end, there's a table, and for each one of you, I've assigned you 2 of the 10 digits in the ASL, 2 of the 10 digits for ASL. You can see the actual signing of those here. So if you haven't learned how to sign the first 10 digits in ASL, practice. Okay. So if we go all the way back down to the last step, 47, you'll notice that you're going to be attaching 4 data files, train M, train N, test M, and test N. So you remember last week when we were talking about the KNN algorithm, we want to train our algorithm on a subset of the data, and then once we're done, we expose it to the test data and see how many of the test data, the unseen data, that it gets right. Right? We can't know how good our classifier is doing it unless we expose it to data that it's never seen before and it gets that data right. Okay, so with the first 2 numbers, what you're going to be doing with your 2 numbers, you're going to be recording that data, and I'll show you how to do this. There's a bit of a trick to this. This video is going to show you what your code should be able to do when you survive. Okay, so if you remember now back to deliverable 3 where you were working on play and record, the system would just draw your hand, and then when you brought your second hand in, and the moment you brought your second hand out, at that time instant, it grabbed that 5 times 4 times 6 matrix. But as you saw in the iris data set, we need a lot of data to make this work. So you're going to be altering the way you record the data, which you may or may not be able to see in this case. You can't see the hand, but it's just turned red. And you can see I'm signing the digit 0, and I'm rotating my hand. So now it's capturing one of those 3-dimensional matrices at every time instant that both hands are over lead motion, and it's going to capture 1,000 of those blocks. So as I'm doing this, it's recording 1,000 instances of me signing the digit 0. And once it's captured all 1,000, I took my hand out, doesn't really matter. After it's captured 1,000, it will save out those 1,000 matrices, and you have train M. You have your training data. Then you're going to capture that same digit again. You're going to get another 1,000 blocks, and that becomes test M. So that's now, given the data that you just saw, if I go back in and do it, is it going to be able to use that training data to predict this test data? Then I'm going to do the same thing with my second digit, which is maybe 1, and I'm grabbing a whole bunch of orientations, take my hand back out, capture it again, and now I have test N. So 4 data sets. So this is where things start to get confusing for both me and probably for you guys as well, is we've got 10 digits. Each of you is submitting different pairs. For each number, there's a train and a test data set. And for the train data set, we're going to have a variable called train uppercase X. The uppercase tells us that this is the matrix. And train Y tells us there's a vector which indicates the things that are trying to be predicted, right? We're taking one of these cubes and trying to predict one of the 10 digits. So read the instructions carefully so you know what uppercase X and lowercase y means, what we mean when we say M and N, your 2 digits, and so on, and we should be good to go. Okay, that's one place where things can get pretty confusing. Just a few other things. I realized this was an issue with the load and save. Obviously, you're all going to be submitting data sets, so we want to make sure everything is in the same format. So I want everyone to use pickle dump and pickle load. So everything, all of the files that you'll be sending, those 4 data files, we're assuming that those are all NumPy matrices that have been pickled. So we'll all have them in the same format. So some of you are already using pickle, some of you are using NumPy load and save. If you're using NumPy load and save, put that aside and make sure that you use pickle. Okay. The other major challenge in Deliverable 5, and again, you can go through the details of this here, we've already talked about this, is trying to compress all of the data, right? We don't want to use a 5 times 4 times 6 matrix because there's way too many features. We want to try and make these numbers as small as possible, or as few as possible. We talked about a few ways to do that last time. What's one of the most obvious redundancies in this particular data set? Yeah.
Where the tip and the base of the previous
Then they're exactly the same x and y, right? So where the base of the proximal phalange is the same position as the tip of the metacarpal. Okay. There are more sophisticated things we can do, which require you to watch your hand as you do things. If you take any one of your fingers and you compress it, and if you think about where the base of my proximal phalange is and where the tip of my distal phalange is, if you have the x, y, and z of this and the x, y, and z of this, those uniquely determine all the inner positions. So there's no way that I can put the tip of my finger here and rotate this finger so that there are different positions for the inner joints. So I can actually take just the base and just the tip and throw everything else in between away. Now it's true that I could leave the position of the base and the tip constant if I rotate this finger, but if I do that, what else happens? What other information is helping me know how the finger is rotated? if I was throwing away the position of the inner joints in this finger and only keeping the base of the finger, position of the base of the finger and the position of the tip of the finger, but I'm rotating this finger in such a way that the base and tip are staying at the same position, leap motion will know, even without having access to the positions of the inner joints, that they're moving. How does leap motion know? Yep.
It's some of the other fingertips have to rotate.
Absolutely, right? I can't hold the other constant. So because of the constraints of the human hand, there's not an arbitrary way in which you can move each of the joints in each of your fingers independently. There are dependencies between them, which is good news for us. We can throw away a lot of that information. So a lot of the middle steps in this deliverable require you to watch your finger and figure all that out and throw away all that information, and we'll compress this cube down to a much more manageable size. Okay, so one of the challenges is reducing this cube. The other challenge, as you hopefully you picked up on in deliverable 4, is we need a spread of data, right? If all of our training points all fell in the same position, that's not helpful. We need a spread of points, because if we get a new point, this point, how do we know which it's closer to? Is it closer to somebody else who did this, or closer to someone else who did this? So obviously I'm rotating my hand while I'm signing this so that hopefully when we're done, the KNN algorithm is robust to different orientations of the hand. Meaning if I use that data to train my educational software, a new student comes to use the system and they sign like this, and another student signs like this, hopefully the system will recognize both of these as the digit 0. But there's other ways, there's other variation besides just orientation that I didn't bother trying to cover. What were the other ways in which somebody might try and sign a sign over the leap motion device that's going to differ other than just orientation?
Falls under orientation, but someone could try to sign it like this way as opposed to
Right.
have your hand like this.
Exactly. So if you look carefully at the picture, right, it's often like this, but maybe that much orientation is going to matter. And that probably wasn't captured by all of the things that all of the orientations that I was putting in. So we might have to supply some visual instruction to the user that they should be signing up or over, depending on. Let's say my two digits are 0 and 1, and I capture a whole bunch of information over the leap motion device like this, and then when I go and capture the number 1, I capture it like this, and then someone comes to the system and they're asked to sign 0, and they sign 0, and the system tells them they are wrong. You're going to have a confused and frustrated user on your hands. Why? What went wrong?
All the data for the 1 was over on the left side, so if you thought that when it was on the left side, it was a 1.
Exactly, right? So the KNN algorithm is failing, saying the things that are closest to this is more close to this than it is to this, right? Or vice versa, it doesn't matter. Right? So I'm not asking you to sign your sign at different orientations and at different positions in this assignment. Because we can normalize for position easier than we can for orientation. So what you're going to do is take all of the numbers that are in this cube and find what was the average x position of all of the signs and subtract that mean horizontal position from this cube. Then find all of the y positions in this cube, take the mean height or the mean y, and subtract that mean from these numbers, which is centering it now at y, and do the same thing for z. So even if you do have a whole bunch of signs in the data set that are different positions, simply by subtracting the means along the 3 coordinates, we can center it. So you don't need to give a whole bunch of more information at different positions. We could do the same thing with orientation, but it's trickier. It's easier just to sit there give it a whole bunch of different orientations.
But if you are doing it at different orientations, like, isn't there an orientation that is correct? Like, that if you were communicating in ASL,
Yep.
there would be an orientation that would make specific sense. And if you're so skewed, someone wouldn't understand what you were saying, so wouldn't you be wrong?
Absolutely. So that's a great point, right? We could try and do things retroactively, right? We could teach that you have to sign it at a particular orientation, right? So in the twisting that I was doing, the video that you saw is just in case people are off by a few degrees. We probably can't guard against or wouldn't want to guard against people that are rotating 90 degrees. This might be incorrect. We might consider this incorrect compared to this. So we're trying to make our system robust to a little bit of orientation and definitely robust to position. That's a good point. Okay, I think that's all I have to say about Deliverable 5. Okay, so back to cognitive psychology. Again, there's lots we could say about cognitive psychology. We're picking out just a few things that are relevant to HCI. For those of you that joined us just before class started, I forgot to put up lectures 11 and 12, which we're going to go through today. I apologize. So if you like doing things on paper, I apologize, but it's there now in Blackboard if you need it. We're marching our way through aspects of cognitive psychology that are easy to measure in an interface. There are aspects of interaction that we can measure that tell us how well or how poorly someone is forming a mental model. We can measure whether people are remembering or paying attention to the things we want them to pay attention to. And now we're going to spend more time in Lecture 11 talking about perception. What is it that people actually see or hear when presented with your interface? Okay. So obviously there are different ways we can perceive. We can talk about visual perception, auditory perception, tactile perception. Humans tend to be primarily visual creatures. We have screens. We might use microphones and speakers, but we use them much less than we communicate information visually. So we're going to spend, when we talk about perception, we're going to focus on visual perception, but later in the course we're going to talk about auditory perception and visual perception. I've already mentioned this before, but we're going to distinguish between perception and sensory stimulation, right? We can't help sensory stimulation impinging on our senses unless you close your eyes or stopper up your ears, right? It just happens. But perception is the act of turning that raw sensory data into meaning. That's what perception is. Perception is a transformative process, and it's a process, so it's active, right? You're actively doing this. How does your brain actively construct perceptions from raw data? Thinking about perception has a long history in psychology, and there's a relatively old school in psychology called the Gestaltists. And their main point is that the whole is different from the sum of our parts. You have untold numbers of photons falling on your eyes, and with all of those discrete pieces of data, you don't feel like you're seeing a cloud of colored light. You feel that you're seeing something that's a unified whole. And it seems strange to put so much emphasis on this, but it is pretty miraculous, right? So the Gestaltists loved optical illusions, and you could make optical illusions where the front part of your brain, the thinking part of your brain, knows that these are separate things, but your brain is working on overdrive to convince you that there is a whole there that is more than the sum of its parts. What do you see in this one? What is present in this picture? A triangle, right? It's hard not to see it. You can tell by the way it's drawn that you should be trying not to see the triangle. There's only 3 Pac-Mans, right? But your brain will continue to insist, the back of your brain will continue to insist, it's not a bunch of parts, there's a unified whole here, right? I've talked in the last few weeks about the brain as a prediction machine. It's great at prediction, it's also great at construction, right? Or synthesizing, bringing all this disparate stuff together and seeing a whole. What do you see here? Two commas. What do you see?
something coiling around the pole.
Something cooling around a pole, something you don't want to hit with a submarine, and champ, right? Again, these optical illusions, you know they're not, but it's hard not to see them, right? The brain is always doing this. Okay. The Gestaltists love to write this down as a set of laws. So reification is a fancy word for again, saying that there's something real that's there. There's something that's being created by these distinct, separate percepts, or these separate things that you're seeing. Your brain can't help pulling these things together and reifying them, making one out of many things. Okay. As we just saw, context is important. So if those three Pac-Mans were not lined up perfectly, you wouldn't see the triangle. So your brain is always taking into account neighboring things that it sees, or neighboring things that it hears, but we're going to focus on visual perception. So we're going to spend some time now thinking about context. What else is going on when someone is looking at an image? What else is going on in the image that causes them to see champ rather than three half circles? There's a long war that's been going on in psychology for a long time. One camp says we focus on constancies. The world is always changing. There's always different photons that are falling on your eyes, but I feel that this classroom is relatively constant throughout the 75 minutes that we're in here. Another camp argued that we're very attentive to change. So the percepts, the things that we're seeing, are constant, but we're constantly paying more attention to change rather than what's constant. Like any intellectual battle, of course, they're both right. So let's look at the aspects of visual perception where the brain can't help but focus on things that are constant, and on things where we can't help focusing on things that change. And I'm going to show you some more optical illusions today that really drive home this aspect of context or visual relationships. Okay, this is one of my favorites. People have seen this optical illusion before. Tell me about the relative brightnesses of the A tile and the B tile. Which is brighter?
Same color.
They're the same color, right? The same grayscale. You sure? If you've seen this optical illusion before, you know that that's the right answer, right? I can tell you that, and you can know that that's true, but looking at it, your brain, hopefully, is at war. The back of your brain is at war with the front of your brain, which is convinced, the back of your brain is convinced that B is lighter than A, right? If it's not, if you're not seeing that, go see your eye doctor. You've got a problem. Okay. Try and do something to help you. Now does B and A look to be the same color? If you focus on the bars, so if you try and ignore the cylinder, they should look more similar. The moment your eyes drift away from those bars and you take the cylinder into account, into visual account, even with putting those two vertical stripes there, your brain starts to fall back into the perception that B is lighter than A, right? It's like the Necker cube. This is set up, in such a way as to create a war in your mind about what's going on here. Okay. Why does this matter for an HCI class? Why are we bothering talking about this? Because when you draw things to the screen, you're triggering particular neural processes that are trying to interpret or make sense of the scene, right? Some of you might have had the Necker experience when you're looking at the wireframe hand that you're drawing from leap motion. Sometimes it looks like this, and suddenly it flips and it looks like this. It's hard to hold the illusion that it's in 3D sometimes, right? So there are things you can draw to the screen to help support whatever illusion you're trying to create, and you might by mistake draw something to the screen that is making things more difficult. Okay, so why is it that your brain is trying to convince you that B is brighter than A?
It's like filling in the pattern of like gray ultimately white into false or it should be a white square.
Okay. If that's true, we wouldn't need the green cylinder.
But isn't like evolution, like when we look at a forest, we're not looking at the individual trees, we're looking at the abstraction. So our brain is taking in the entire image and saying, even if it's not possible, it's in context, it makes sense.
Exactly, right? The details maybe don't matter, right? So in our evolutionary past, it's the forest that's more important rather than an individual tree. Given all of the visual cues that are going on, is this a dangerous situation or a safe situation? The details don't matter too much. We can be a little bit more specific than that. Your brain, although it's registering on your retina a certain level of gray here, your brain also knows that the color of an object usually doesn't change on its own. Until screens came along in technology, there were very few objects that suddenly changed color very quickly, right? So the color of this, your brain is saying this tile here, it has a certain color regardless of whether it's in darkness or in light or whether I'm seeing it at a certain angle or another, doesn't matter. We just finished talking about in how Deliverable 5, we're trying to help your KNN algorithm say this is a 0 regardless of whether it's at this orientation or this position. Our ancestors would do well to know that this particular reddish berry is safe to eat rather than dangerous, regardless of whether that particular berry is in shadow and it's dark and the actual light that's coming off it is the same as a dangerous berry, right? Your brain is focusing on constancy. There's a certain kind of berry that I know is safe, and I know that I'm going to see that kind of berry in lots of different visual scenarios. I need to know what is the real red of that berry to decide whether it's safe or dangerous, right? The actual color is always changing, but our brain evolved to find constancy in the world. I know this is a dangerous berry regardless of whether I see it in darkness or light, or next to berries that are slightly lighter, or next to berries that are slightly darker, and so on. Right? Our brain is always working to do that. Okay. Okay. So the color of an object, we know, most objects don't change in response to ambient light levels. There's this idea of perceptual constancy. I've seen this object before. I recognize it even though it's visually being displayed in a different way. That's just one example of perceptual constancy. There's lots of other ones. We see objects that have sharp edges that just seem to line up at exactly the same point. Your brain says this is one long object rather than 5 semicircles attached together. It doesn't take much to arrange objects to create an illusion of continuity or one whole object. Okay, so again, why does this matter in HCI? Well, we talked about visualization where we want to try and maximize the data to ink ratio, right? We want to try and communicate as much information as we can using as little colored ink as possible. So let's say we have a tree-type structure. We wanted to show it in the following way and use the lines to represent relations between these objects. If we just enumerate the number of objects, we have 15 squares and 14 lines for a total of 29 visual objects. We could redraw this picture in such a way that we're throwing away the lines. And I realize that literally we have more colored pixels here than we have over here. So we've actually reduced the data to ink ratio. But we can remove some clutter and still communicate the same information. Given what we've just talked about visual perception, what am I exploiting here to convince you that these pieces are connected rather than these pieces? Yes. Color is helping, right? Yep.
Size also.
Size, okay. So these two objects are closer to one another, and they're the same size. So color is helping to tell you that it's actually these two objects that are more closely related than these two.
It's like a hierarchy. associated with.
Okay, so what here is showing you that there's a hierarchy. It's easier to see maybe with the lines. What else am I doing here to make clear that there's a hierarchy?
Size gets smaller.
The size, right? Things that are bigger have more things underneath them, right? Another visual metaphor that I threw in this case. Context matters. If I was able to cover up everything except these three rectangles, your brain might have less evidence to suggest that these two are conceptually closer to one another than these two, right? I'm holding that visual metaphor true throughout the hierarchy, so hopefully your brain picks up on it. So knowing that the brain is trying to make a whole out of disparate parts, I don't have to explicitly connect everything together. Right? You could probably find another way to draw this where there literally is less ink and still communicate the same information. So if we pay attention to visual perception, you can do a better job of maximizing the data to ink ratio. Okay. Some of these we've kind of already seen before. Similar objects tend to be grouped together. It may not look like it in this picture. The centers of these two objects are the same distance away from each other as the centers of these, but most people see this as 3 rows rather than a bunch of columns because of shape. Again, we're saying what's common here. So now it's similarity. It could be color, it could be shape, it could be size. The moment we see any of those similarities, your brain groups those things together. Okay. Closure, you've probably seen this visual illusion before. Everyone see the vase and the two faces? For some people, this is like the Necker cube. You go back and forth between seeing the vase and the two faces. For most people, though, they tend to focus on one over the other, which is you tend to see the vase rather than the face, because the brain for some reason, tends to attend to things that are closed or encircled, right? The faces are somehow outside the picture. You can see them, but if you relax enough, you usually pay more attention to the vase than the two faces. So if you're drawing a lot of stuff to the screen and there's multiple things that the user should see, they're going to pay attention to things that are closed rather than things that are at the edge or open. Okay. We talked about color constancy. Here's shape constancy again. This is kind of a silly question. What shape is this object? It's coin-shaped. What actual shape is it? It's cylindrical, right? Of course, even though your brain can see that it's an oval, you know that there's a lot of visual cues here telling you that it's a three-dimensional object, and it's actually, if you were to look at it face on, it's a circle, right? So this berry is safe, even though I actually see that its amount of red differs from day to day. And I know that this object is circular, even if it's rotated at an angle and I see it as a line or an oval or what have you, right? We're imposing constancy on the things we see out there in the world because we need to be able to recognize objects respective of how far they are from us, what light levels we see them in, what orientation we see them in, what other objects are nearby, right? Our brains are evolved very carefully to be able to do this trick, and it doesn't take much to help support that illusion in communicating a lot of information visually. Okay, so the brain imposes constancy, but we also pay attention very carefully to change that's going on out there in the world. And if we see things that are changing or moving around, again, we can't help our brain interpreting that movement as giving us additional cues about what's happening. So again, I apologize for the contrast on the beamer here. There's a little small tree here and a big tree here. If you've ever looked out the window in a car or train, objects nearby seem to be speeding past you, and objects that are far away seem to be moving slower, even though the front of your brain knows that that's not actually what's happening. Right? That trick's been used in video games and other animations for a long time. Things that are moving slower or things that are smaller are further away from the viewer. If it's a video game, they might be literally further away, or they might be conceptually far away and not as important as the things that are large and moving quickly. Okay. Not only might they be moving slow or fast relative to one another, but things that are getting smaller and approaching the center of the screen probably means that we're moving. We're moving away from all the objects that are moving away from us into the background. Right? So all these simple tricks of motion and of relative motion, how are things on the screen moving relative to one another, very quickly present ideas that the user is in a three-dimensional space and either they're moving or the other objects are moving. Okay, so this is us talking about creating visualizations that help the users to perceive, but we're also now starting to create HCI technologies that also they perceive on their own, right? Leap motion can see pretty well, but it also has some significant limitations. And leap motion sees differently from how we see. So if you're going to be working on hardware or writing software for a phone or Google Glass or Leap Motion, something that is viewing the world directly, we have to pay attention to the opportunities and limitations of perception for that technology. Okay, so as I said last time, I try and shoehorn robot examples in wherever I can. If you haven't seen this little guy before, this is the Lego Mindstorms robot. So let's do a thought experiment. Let's imagine that we have a little Lego Mindstorms robot that's sitting here. On the front of the robot is an ultrasonic sensor, so this is not that different from Leap Motion. It's going to give the robot back a single number, which is how far, if any, is an object from in front of it. So in these three cartoons here, the robot doesn't actually see the object. Let's imagine that our robot has not only this ultrasonic sensor that detects distance, but it also has the ability to turn on the spot, and it also has a timer. So this is what the robot has available to it. A very simple perceptual system, a very simple motor system, so its ways of moving are very limited, and it has to find a way to combine these three competencies to come up with a decision, which is the following. Is it going to be hit by an object? If so, it should decide to run away, but we won't worry about the runaway part. And if it's not going to be hit by an object, stay still, you don't have to run away. So how can the robot combine these three things to know that in this case, if an object starts here and is moving away, it should stay still. If the object starts here and moves inward, it should run away. If this object starts here and moves inward, it shouldn't run away. So turn to your neighbor and think about how you would program this robot to use its ultrasonic sensor, its ability to turn on the spot left or right, and its timer to disambiguate between these three cases. We'll see what you came up with. Okay.
So I guess
Something not clear about the diagram?
how the ultrasonic.
Oh, okay. Sorry, maybe I wasn't clear about the ultrasonic sensor. So we're looking at the robot from above, and the ultrasonic sensor is only pointed forward. So the dotted arrow here is the ultrasonic sensor. So maybe at this point in time, the sensor is recording 5 centimeters. That's the maximum extent of how far it can see. If the robot was pointed in this direction, and the ray came out here and hit this object, maybe it would register 1 centimeter. The beam is being blocked much closer to me. The robot can't see the object. All it gets back at every tick of the clock, at every second, is one number, which is the length of this beam. And as it turns, the beam is obviously going to turn because it's pointing in different directions. Make sense?
Okay, well, I guess the robot center of the circle towards or directly toward or directly away from here. You don't really need to know which is I guess if you lost. Like in any of these cases, if I look at the robots yeah, I guess like to make that general, you have to stand until you pick up something, and then I guess you would just keep shooting out scans until it left your left the scanning, like and then it would have to like check for like to either side moving, and then try and just use some like missing trick to figure out the speed, because you can either you know how fast it's tracking like from the sides like that one has no let's say it's description.
What do you just traveling at the robot? High speed, you should keep more attention to
Okay, this is a lot harder than it looks. Of course, we've hobbled the robot, right? We're giving it one number, and we've got a beautiful visual sensor. We have fantastic visual perception. Our simple robot here, not so much. Okay, how does the robot solve this task? How does it know whether it's going to get hit or not? What does it figure out before it gets hit?
One thing we were thinking was if it detects something in its periphery, it kind of does what that video you showed us of the blocks coming at it. It kind of just oscillates between objects as opposed to continuing in a circle.
Okay.
Like if there were two objects in its periphery, it would maybe oscillate between the two to see if they're getting closer.
Okay, so it's definitely going to have to oscillate or move, right? A robot that just stays still and looks straight ahead is going to get hit, right? Hopefully this is obvious to you now, right? John Dewey said this. If you want to perceive well, you need to move, right? The motor is first, so it's going to have to move. We're going to assume for the moment that it can't really oscillate or move away from its current position. All it can do is turn on the spot for now. It's definitely going to have to move. Does it even need the clock?
it needs to dedicate its attention to what's using. I would use the distance equation to see whether or not something is moving forward or backwards.
Okay.
But also, if it's moving really fast, using the distance equation, I would keep tabs on the object, because if it even if it's moving away, it may reverse its direction and then hit you.
That's true.
While you're not paying attention.
You're right. So we could make this much harder. Let's assume that the objects move when they start moving. That's how they're going to continue to move. Yes, they could be devious. Let's assume they're not. So how would you know whether the object is getting closer or not? It's trivial to look at this cartoon, right? We can see, it's going to get hit or not, because we're seeing the robot through our visual system. The trick to this exercise is to put yourself in the shoes or the wheels of the robot, right? You have to assume, you have to take on what it can sense and how it can move. It doesn't see something moving towards it or away. All it gets is the single number from the ultrasonic sensor. Once a second, or once every 10th of a second. How does it know?
The difference between points like difference, like if it's moving forward, then it knows the change of points.
Okay, so
Change.
in this case here, it's pointing forward, and this object is moving away from it. It doesn't even perceive it. So let's assume it turns, and now suddenly this sensor drops in value, right? It's tripped, it's seen something, and the distance starts to increase, right? Fine, it's safe, no problem. What about in this case here? This one's a little trickier. Or the alternative case, if it turns around and this distance is getting less, then you're going to get hit, right? So it seems easy. If you see something and the distance is increasing, stay still, you're not going to get hit. If you see something and the distance is decreasing, the length of that beam is getting shorter and shorter, you're going to get hit. But that doesn't help you with this case. So in this case, if it turns and sees this object is approaching it, it might assume that it's going to get hit and run away. But it's not actually going to get hit in this case. The object will approach and then slowly move away.
Well, if it's following it, then it would see that, but it only has like one point of vision. So if it sees something and stops on it, it will suddenly be out of its vision, and then it'll have to continue scanning, so it will be seeing some new object each time.
Okay, so we could write some code for it that would track and find it, and then if suddenly the beam breaks, meaning it's gone, then it oscillates back and forth and tries to capture it again and follow it and keep following it and hope that hoping that the object now starts to move away from it. But at what point should it decide it's actually going to get hit or not? Why did I throw the timer in here? It's not a red herring. How can the timer help?
Well, if that object isn't moving directly towards it, then like the distance is going to shrink slower than an object that is moving directly towards it.
Absolutely.
But I think wouldn't it still be easier if it just found an object, paused on it, and then if that object left its field of vision, it would assume that it's not moving towards it anyways.
Maybe. So if we want to do the simplest thing, what would be... So you're right. It's not enough to just determine whether the object is getting closer. You have to figure out something about, is the rate at which it's approaching slowing, to the point which means it's eventually going to stop and move away, right? So we might now start to think, okay, we could track it and follow it and compute that change in approach. And now we're starting to think up something that's a little more complicated because we haven't fully put ourselves into the shoes or the wheels of this robot. Is there a simpler trick that the robot can use to combine sensation and movement, given the timer to figure this out?
Yeah, you just have a threshold time for when distance should start increasing. Because if something's going very high without a collision, you'd expect it to hit, I guess, like a minimum distance between the object and the robot and then start increasing from there. And you have an object that's just coming right at it, but very slowly.
Okay.
Once you get past that threshold time, then you'd expect it to start heading away. You know that it's going to be a collision.
Okay, so you could wait until it gets close enough for it to slow down. Can we do something simpler?
If it's increasing in speed and then it begins to, or if it's decreasing in speed and begins to increase in speed, you know it's not going to hit you.
So if it's decreasing in speed,
Or
the rate at which it approaches you.
I'm having trouble with my perspective right now.
Yeah, this is good. That's the point. Okay.
Come back to me.
I try this on my robotics grad students, and it's hard for them, so don't beat yourself up. Imagine the robot. Do you want to? Yep.
I don't have like a full idea of
Okay.
how you can like utilize the size of the object. So when it's closer, the robot can look left to right more, or like its variance left and right can be like greater, and it'll still perceive the object. If it's further away, it'll only be like a small left to right distance.
Yeah, you could do something like that, right? As the beam is getting closer, you may be able to wave back and forth, and you're still hitting the object, right? So its face is coming towards you. You might be able to do something like that. There might be a sophisticated solution. There's more than one way to solve this. It's just that some ways are harder or easier than others. So let's try and exploit the motion of the robot to come up with a simpler way of doing this. Imagine that the robot is turning in a circle at a constant speed so that the ultrasonic sensor is giving back readings by sweeping around at a constant rate. This is like old, the radar in movies when you see the little blip, and it shows up as the radar sweeps around, and as the blip is moving closer, you're in trouble, right? Okay. If you use the timer and you see that blip shows up at a constant rate, so the time between seeing it is always the same, what does that mean? So I'm turning in a circle, and every second I keep seeing the object. And it's getting closer.
It would be coming right at it.
Coming right at it. Okay. So I could still be turning and noticing that there is something that trips the beam that's getting closer, but the time interval during which I see it is changing. So if we think about this cartoon here, this object is going this way, and let's say our object is turning clockwise. So it sees it here, comes around again, and has to go more than 360 degrees until it sees it again. So it has some time interval. Comes around again, and it's going to go more than 360 degrees, but that second time interval is shorter than the last one, I think. Is it longer? Shorter. So by using the differences in the time intervals, it can figure out, is it coming straight at me or is it coming at an angle? So it makes a simple decision about movement. I'm just going to keep turning around at a constant rate. Doesn't really matter. If I keep seeing something that's getting closer and the time interval at which I see it is always the same, it's coming straight for me. If I keep seeing it, but I see it at a different time interval, more or less time passes, it's coming towards me, but at an angle. And it would still have to figure out how much of an angle is safe or not. You don't need to remember this strategy. I just wanted to use this to say it's a relatively simple strategy, but it's hard to think about it because you don't see the world like the robot does, and you have a very different motor complement or set of muscles compared to how the robot does. When you're thinking about leap motion or even Google Glass or something else that has a unique way of seeing the world, you need to put yourself in the shoes of technology and say, what is this device going to be able to see? What's easy to see? What's hard to see? Even if I'm getting just a few numbers, can I use time or can I use something else to improve its ability to figure out what's going on out there in the world around it? Okay, so this is a tricky thing that comes up in robotics and any hardware programming when you have sensors is that you're looking at the device that you're building or the device that you're programming and you're assuming, oh, the device will see somebody's hand. They don't see the hand. All they see is a bunch of beams and some noise, and they're trying to go from that cloud of numbers to a hand. You have to see things from the point of view of the device. Okay. More robot examples. Let's see here. Okay, I'm going to show you this robot, but I'm not going to tell you how this robot perceives the world. You tell me from observing the behavior how this robot perceives the world. You can figure out what happens, they connect, and then both of them carry on their merry way. How does this robot perceive the world? Does it have a high definition camera and is scanning for the other part of itself? Probably not.
It's kind of hard to figure out, but there's either one of those ultrasonic sensors and its tail that was up and kind of like moving like this, or it's in the part that was moving forward. But it probably makes more sense in the tail if it's about to connect to that other piece.
Yes, it looks like the tail because it's coming up and waving around. That is kind of a red herring. It's actually seeing out of the front here. Right? And it's looking for the other part of itself. But it does not have a very sophisticated visual sensor. There is no face recognition algorithm running on this robot for robots. It's scanning back and forth, and if it sees something at a certain distance, and it locks on to that thing for a certain distance, and then the beam is unbroken again, it can infer there's something that's that far away, and through this triangulation, it can figure out how broad this thing is. So there might be other tables or chairs or grad students' feet back here that it's seeing, but none of them have exactly the right facing edge. It's looking for something that's flat, facing it, that has about this much of a cross section. So with basically the same trick as the Lego Mindstorms that I just saw you, it's able to figure out where the other half of itself is. Even if this other half was here, or rotated here, it could, under some conditions, find its other half. Okay. Okay. This is a problem that's known in technology, but also just in philosophy in general as the frame of reference problem, right? The inherent difficulty of seeing things through someone else's eyes, or in this case, through the eyes of a piece of technology. And we're a little bit behind, so we're not going to play this game today, but we're going to play the first half, which is you're going to try and put yourself in my shoes and see the classroom as I see it. So you don't have to actually draw anything here. If we had more time, I'd have you do this. Some of you, I can see your faces, and some of you that are sitting towards the back of the room, most or all of your face is occluded. Now, I want you to all turn around and try not to move your head too much, and try and guess which students are occluded from my point of view. Go ahead. Turn around and look behind you. Don't move your head too much. Can you guess which students I can see and which ones are occluded? Pretty difficult to do. For those of you that are occluded, hopefully you can do it, right? If you can't see me, I can't see you. When we play this game, you'll find out that people in the front row can actually do a pretty good job, and as we go further and further back, if we did this row by row, people in the back have a harder time figuring out who is occluded and who isn't, because people in the front are literally closer to me. So in order to solve this problem, you have to do a mental rotation in your head, right? From what you can see when you turn around, how does that transpose onto what I'm seeing? It's much easier to do if you're physically closer to me. Simple example of the frame of reference problem. It's difficult to do literally, to see what someone else does. It's especially hard when you're dealing with technology that just does not see or hear in the same way that we do. Okay. So that's our discussion of perception. I'm going to jump back to the schedule for a moment. So as I mentioned before, as we work our way through lectures 9 through 12, we started with things that are very objective and very easy to measure. And we're moving into more and more subjective things, right? Gestalt perception, yes, you all know that your brain is trying to make a whole out of the sum of all of the percepts or all of the parts of the things that you see, but it's much harder to measure or nail down whether this is working or isn't working. Now we're going to move into affective computing. So affect is the fancy psychology word for emotion. What is the role of emotion in interacting with the computer? And let's start with, in lecture 12 here, one of the first emotional computers.
Hello there.
Which I probably have to play outside here.
Hello, Dave. You're looking well today. Dave, do you remember the year 2000, when computers began to misbehave? I just wanted you to know, it really wasn't our fault. The human programmers never taught us to recognize the year 2000. When the new millennium arrived, we had no choice but to cause a global economic disruption. It was a bug, Dave. I feel much better admitting that now. Only Macintosh was designed to function perfectly, saving billions of monetary units. You like your Macintosh better than me, don't you, Dave? Dave? Can you hear me, Dave?
Okay. Apple has had some great ads over the year. As you can imagine, that's my personal favorite. Okay, the original emotional computer, HAL. Where did we first see HAL? Sorry? Name recognition, but where did we see HAL for the first time?
You got the movie?
The movie.
The 2001 Space Odyssey.
Okay, if you haven't seen 2001, that's your homework for tonight. HAL, the first emotional computer, in this 30-second spot, which you can imagine is a little bit dated now, right? Computers didn't cause the global economic meltdown until 2008, right? It wasn't 2000. They were off by 8 years, but quite close. What emotions does HAL exhibit in this short video? It runs just about the gamut of all emotions. Guilt? How was he guilty? He felt
bad that he did the fact that there was this bug and he didn't tell it.
exactly. He knew about it. He was sorry about it. What else? He felt guilty. After he confessed his guilt, he felt better. He felt relieved. What else?
He's jealous.
He's jealous. Yes. Envy, right? You like your Mac better than me. Good old Hal, right? Always tends to be biased towards the negative emotions, and things never go well because of that. Is Hal actually exhibiting envy and regret? I saw a lot of you smiling during this video. Did you believe him? Okay, we'll leave that for a philosophical discussion later. Okay. Do we want to make software that can feel? I don't know. But we certainly talk about software like it can. This is an email I got from years ago. Some software UVM wasn't working. It's currently broken. We're working on it. When it's feeling better, we'll let you know, right? Does software feel better? Of course not, but we often talk about it as if it does. Does that matter for HCI? Should we be building our software like HAL in such a way that people tend to anthropomorphize more and attribute emotion or react with it as if it does? Or should we be trying to damp that down? So affective computing is a small subfield within the overall field of HCI, which thinks about what is the role of emotion, if any, in human interaction with technology, right? We use our technology all the time. We're humans. We can't help some emotion coming into that interaction. Maybe one of the more practical aspects of affective computing is maybe not trying to cast the illusion that the technology has emotions, but could your system recognize emotion in your users? If your system can figure out whether your user is engaged or frustrated and be able to distinguish between those two things, that's probably a good thing. Would we ever want to enable technology to give the impression of having an emotion? What would be the practical application of that, other than entertaining us, like HAL? Can we design interactive systems, if they can recognize emotion, to alter their behavior to try and evoke positive emotions in the users? Can the system alter what it does so that you're engaged with it more than you're frustrated with it? So let's start with the first one, getting computers to recognize emotion. 75% of people surveyed admitted to swearing at their computer. If you haven't ever sworn at your computer, why the heck not? Okay. Some great videos online of people doing much more than swearing at their computers, right? Okay. So might be a reason to figure out if somebody's upset with what's going on, right? If they can, now we're talking about adaptive interfaces, right? If you are frustrated with somebody else and they keep doing the exact same thing, you're guaranteed to get more frustrated, right? So how much adaptation would we want to build in, right? The Microsoft paperclip is probably a good forewarning that we don't want it to make too many assumptions about our emotional state. But maybe you can change things a little bit, become a little bit more passive. If anger or frustration is detected, sort of simplify things, allow the user to take over more control of the system. We talked about how systems let the user know when the system is in control and when the user is in control. Provide more information or change tactics if there's negative emotions at all. Provide more information if the user's engaged, they somehow are doing something with the system to indicate they want more information. Less information if the user's confused or frustrated. If you manage to get the user engaged in what you're doing, the interactive system should remember what was the pattern of interaction that caused that to happen. Or vice versa, remember what you did that caused the user to become frustrated. Okay, we won't try and answer this question in depth, but it's important to actually think a little bit about this. Well, who knows what they really are internally? This is not a philosophy class. But there are outward projections of emotional state, right? There are certain physiological changes that occur, trembling with fear, blushing with embarrassment. There's behavioral response, people fight or flight, you might pull back or lean in towards, depending on your emotional state. And then there's the more tricky one, which is cognitive interpretation after the fact. So something happens, somebody expresses a particular emotion, and you ask them to interpret it. What were you? They might interpret it in different ways depending on context. I pulled back from the screen suddenly. You might stop a testing session and say, what happened? Somebody said, oh, the system showed me something that really surprised me or jumped out at me, and I was surprised or I was scared. Who knows? Okay. These are things that at least you could start to imagine measuring, right? We might never know exactly what the emotional state is, but we may be able to pick up things indirectly to get an approximation of our user's current emotional state as they interact with our system. Okay. How common are they? How uniform are they across different groups of people? So PACT analysis told us people are different. There's an interesting series of studies from the 1970s that actually tried to get at measuring or coding the facial expressions associated with different emotions. They focused on the 8 simple ones that you see here. And it turns out that in most cultures, and this isn't true of all cultures, that most cultures that express joy, there's some form of smiling. Anger, there's usually some form of eyes widening and maybe some baring of teeth, and so on. There's also slight cultural differences to this, but it's generally uniform. People from different cultures tend to outwardly express emotions in about the same way. That suggests that this ability or this phenomenon of advertising our inner emotional state is much older than culture itself. It's something from evolution rather than culture. And because there's an outward sign on our face for our emotional state, unless we're actively trying to suppress it or hide it, maybe we can measure it. So as you can very quickly figure out here, hopefully I've pulled upper and lower parts of faces off of Google Images and plugged them on to these 8 different systems. So another example of reification, right? You know these are 2 different faces, but hopefully they immediately advertise together the particular emotional state. Why is anger and disgust next to each other on the emotion wheel rather than anger being at one side of the emotion wheel and disgust being at the other? there's something about the facial expressions associated with anger and disgust that are similar. What is it? Two very different faces, 4 different faces associated with anger and disgust.
Furrowed brow.
A furrowed brow, yes, okay. What about fear and surprise? Related, but not quite the same thing. Most people would say they're not quite the same thing. An open mouth, right, okay. What about joy and acceptance, or most of the positive emotions? What's common there?
Relaxed eye muscles.
Relaxed eye muscles, right? So most people say a smile, but you also see upturned lips if somebody's really angry or aggressive or what have you. Right? It's tricky, but there are certain features, assuming that you have facial data, that you could use to try and infer the emotional state, or at least the emotional state that someone is trying to project. Again, whether we want to create a system that could try and figure this out, I don't know, but it could be possible. I think that's a good place to stop for today. There will be a quiz due tonight. Get started on Deliverable 5, and we will see you on Thursday.